Hello! I want to thank the organizers for this opportunity to present the keynote, and I also want to thank all of you for listening in. What I'd like to do is present 4 different ideas. Minerals first are thought to have played key roles in life's origin. Mineral surfaces interact strongly with organic molecules. Minor and trace elements may be key to understanding prebiotic chemistry. And finally, we need to rethink what we mean by mineral species. Now, these 4 ideas seem rather disjointed and unrelated. I want to try to tie them together in the next 10 minutes. So, first of all, minerals are thought to have played essential roles, key roles in life's origins. Things like catalyzing reactions and templating, scaffolding different molecules, selecting and concentrating different types of molecules on mineral surfaces, serving as reactants, and even just as protective environments for delicate molecules. All these ideas are out there, and particularly I want to focus on this role of minerals as possible the first enzymes. There are many different types of molecules that act as enzymes that do oxidation reduction reactions, like the aconitase enzyme. And in each of these types of molecules, there's typically a core or the transition metal that serves as the electron transfer site. So for example, in nitrogenase, we have early nitrogenases with just iron. Later, because of the geochemical evolution of the oceans, there's iron and molybdenum combined. These kinds of molecules then appear to have little clusters which almost look like minerals or mineral surfaces. These ideas of the role of minerals have been expanded by Steve Benner's group, who have looked at very detailed chemical reaction pathways that require borates or molybdates or other exotic sorts of mineral-like intermediaries in order to accomplish these reactions. Though I don't expect you to look at all the details of these charts, you can look at the original papers, but the idea here is that there are very key and selective roles of certain elements. Okay, so that's the first point. The minerals may have played an important role. The second point is that organic molecules often interact strongly on mineral surfaces, for example, through chiral selectivity, left and right-handed molecules concentrating on different faces of mineral surfaces. Now, we've been studying this kind of phenomenon for a number of years in our laboratory. We do potentiometric titration and batch absorption experiments, and what we find is that you can see very clear reactions of these molecules. They absorb strongly pH dependent, it's dependent on the concentration of the molecules, and their different configurations of absorption, and it's easy to see how molecular assembly and other steps in life's origins might have taken place on mineral surfaces. So that's the second point. But you have to ask what minerals were present during Earth's Hadean eon. We've been studying this for some years. There was a preliminary list published in 2013. It was expanded in 2019 by paper in Morrison et al. And we really think then, if you're going to invoke minerals, were those minerals present in the Hadean eon when life is thought to have originated? So many of the minerals people talk about, sulfides and clays and so forth, were certainly present during the Hadean eon. But others, borates and molybdates in particular, it's very difficult to rationalize those as being important in the origin of life because there just simply weren't a lot of borate or molybdate minerals. Nevertheless, if you think now about trace and minor elements in common rock-forming minerals, maybe we have a solution. So here's the crustal concentration of some of these elements like cobalt and nickel and phosphorus and boron. Now, not very impressive, but if you look at common rock-forming minerals, which are just everywhere, they have an ability in some cases to concentrate by more than an order of magnitude these rare elements, and therefore provide surface sites where chemistry can be done. So here's a conclusion. Key elements are ubiquitous. Nickel, cobalt, molybdenum, boron. They're not represented by common minerals, but nevertheless, they're ubiquitous as abundant minor elements in common rock-forming minerals. Now, this is an obvious point, but for decades, origin of life people have missed it. And why is that so? And I think it's because we need to rethink what we mean by mineral species. So the International Mineralogical Association says a species is naturally occurring. It has fictive end-member chemical composition, such as SiO2, has an idealized crystal structure. What that really means is that IMA is saying, let's define minerals with the minimum possible number of bits of information. A fundamental aspect of minerals is that they're incredibly rich. in information. That's how we can understand evolution. We can understand history through looking at minerals. They preserve that history because they contain immense amount of information in their trace and minor elements, their isotopes, their defects, their inclusion. And so we should expand the IMA protocols with a new kind of classification system. In some cases, we're going to split minerals into several different natural kinds, and others we're going to lump them into one natural kind, and we're also going to recognize and embrace the amorphous and non-crystalline phases, which are so important in geology, but simply can't be handled by IMA because they don't have a well-defined structure and composition. So think about pyrite, FeS2. We have hydrothermal vein pyrite, we have low temperature pyrite, we have biogenic pyrite. There may be many different kinds of pyrite, each one with a different history, a different paragenetic mode. They shouldn't be treated as exactly the same thing. On the other hand, there are over 30 IMA species of tourmaline, but there certainly aren't 30 different ways that tourmaline form. And in some cases, as in the work of Ed Grew, you see an individual 100 micron crystal that has multiple species simply because of zoning as the crystal grew. And then finally, we have things like obsidian and coal and limonite and pyrolusite, materials that aren't considered by IMA, but we think need to be considered just the surface of Mars, where in some cases, Curiosity is finding up to 70% amorphous materials in Mars' surface. They're just not considered by IMA, but we need to. So we think there's a new system of mineralogy that's needed, and the key to this evolutionary system of mineral classification lies in all that information, the multidimensional attributes of minerals. This idea was presented in 2019, and we're now moving ahead using various kinds of approaches, including natural kind clustering. We have a very large database of pyrite, 8,000 pyrite analyses with multiple trace and minor elements. Indeed, those very elements which are so important to the origin of life in some cases. And when you analyze these in multi-dimensions, you find that they fall into discrete clusters depending on where and how the pyrites form. So we have a team of people looking at pyrite and garnets and moissanite and some other minerals. We can apply this to the evolution of minerals in the cosmos. The earliest minerals formed around stars, asymptotic giant stars or exploding stars, other kinds of stars. And each of these environments, these stellar environments, created different combinations of isotopes, which are amenable to cluster analysis. So our first paper in the series, part 1 of stellar mineralogy, looks at different minerals. For example, graphite from supernovas, and there's moissanite from AGB stars. And we represent these different kinds and combinations of environments and minerals in what's called a bipartite network diagram. These are helped with us. Anirudh Prabhu at RPI has helped put these together. And what you'll see is two different kinds of nodes in this diagram. Some of them represent different kinds of stars, like supernovae and AGB stars. Other nodes represent different minerals, like graphite or moissanite, linked to multiple different stars. So each star is linked to multiple minerals, each mineral linked to multiple stars. We can expand this by thinking about solar nebulae and primary condensates. More minerals pop up. We can add interstellar clouds, and here we see the ices forming in that interstellar environment. We can expand this to other meteorite minerals, the primary chondrule minerals, the CAI minerals, for example, and even the secondary minerals, the aqueous alteration and shock alteration forms. And we can imagine this moving forward as we develop this system of mineralogy with more and more thousands of minerals, dozens and dozens of different kinds of paragenetic modes, and eventually all of mineralogy represented by this one kind of interactive diagram. These diagrams are being presented in a series of papers. Part 3, Part 4, Part 5 are in review or in preparation. And our conclusions. Mineral-molecule interactions likely played key roles in life's origins. Ubiquitous trace and minor elements in common rock-forming minerals obviate the need for exotic minerals of rare elements. And finally, this new evolutionary system in mineralogy embraces data-rich attributes of minerals and provides an alternative classification approach. With that, I want to thank our funders, the Keck Foundation, the Sloan Foundation, NASA's Astrobiology Institute, the Rutgers Enigma team, Templeton, Carnegie, and thank you very much for your attention listening, and I hope there's time for a few questions.